We have a clustering system. It produces k clusters. I'm going to call them C1 through Ck. And let's say that I have a set of reference clusters. Maybe they're digits, or maybe they're classes, or maybe somebody just clustered the data set, and that's what I have to reproduce. So I have a set of reference clusters R1 through Rn. And note that the number of clusters that your system is producing and the number of reference clusters doesn't have to be the same. In most situations, they will actually be different. So how can you evaluate if you have a set of reference clusters and a set of system clusters? The basic evaluation works like that. We're gonna pair up the clusters that our system produced with the reference clusters. So introduce some sort of a pairing. And then once we have the pairs, we can do our normal evaluation. So what we talked about, the basic building blocks, the true positives, true negatives, false positives, and false negatives, we can compute them once we have a pairing, right? So if cluster 1 in the system output is paired with reference cluster 2, then I can draw a Venn diagram and I can see how many elements are both in cluster 1 and in class 2, so that's your true positives. How many elements are only in cluster 1 but not in class 2, that's my false positives, and how many are only in class 2 but not in cluster 1, those are my false negatives. So if I have a pairing or an alignment between system-generated clusters and reference clusters, I can compute my basic building blocks and then construct any evaluation metric I want out of those building blocks. So it's straightforward once you have an alignment, but it turns out that creating this alignment is not entirely trivial. You have to be careful in how you create it. And by the way, why is this an issue at all? Why am I not just connecting C1 to R1 and C2 to R2 and C3 to R3? Could I do that? Why not? So suppose I have the same number, I have 10 clusters, and I have 10 classes that correspond to digits. Why can't I connect cluster 1 to digit 1? To the class that corresponds to the digit 1. Why can't I just do that? Yes, so the answer is it might contain the wrong class. Keep in mind, the clustering system, it has no idea about your classes. It's an unsupervised task. You just give it a bunch of bitmaps and it's going to cluster them. What it calls cluster number 1 is completely arbitrary. It could be digit 1 or it could be digit 7. It could be anything. Right? Your clustering system is unsupervised. It doesn't know about the classes. So there is no obvious natural way to line it up. Right. So how do you line things up in practice? What Weka, the system that you are working with, does is it constructs a little matrix of overlaps. Right? So it takes all the clusters that you've generated. I have 4 clusters in this case. It takes the reference clusters, so I have 3 in this case. It computes an overlap between each system-generated cluster and reference cluster, basically how many elements are both in the cluster and in the reference class, and then it does the alignment based on the maximum overlap. Right? So it goes over each cluster and picks the class which has the highest overlap with that cluster. So in this case, C1 has the highest overlap with class 2, so it would align C1 to class 2. C2 has the highest overlap with class 3. C3 also has the highest overlap with class 3, so it would initially assign C3 to R3. And then C4 has the highest overlap with class 2. So that's the initial, assignment. Now what it does then is it reassigns them to avoid multiple assignments. So look at what I have. The class R2 is assigned to 2 different clusters. It's paired with cluster 1 and cluster 4. And class 3 is paired with cluster 2 and cluster 3. And that turns out to be a problem, and we'll talk about why that is a problem. So you need to get rid of that. You cannot have multiple alignments in a contingency table. The way Weka gets around that is it reassigns, it starts moving them around in a greedy manner. So what it's going to try to do is it's going to say, well, okay, so C2 is currently assigned to class 3, right? Can I reassign it? And as I reassign it, I'm going to lose some points in the overlap. But what is the smallest number of points that I can lose as I try to reassign things? So what it might want to do is it will take C2 and align it to class 1 now. Right? So you're losing 1 point there, but that's the smallest. It wouldn't be any better if you moved C3 or if you moved well, if you moved C1, it wouldn't help at all. And then you have C4, which is assigned to R2, and C4 you can't even move anymore, right? Because there is no more reference clusters left. So C4 is just not going to be assigned to anything. You have a choice of either dropping C1 and then you would lose 3 points, or you drop C4 and then you would lose 2 points. So it'll drop C4 in this case. And the final alignment is going to look like that. C1 is going to be aligned to R2, C2 is going to be aligned to R1, and C3 is going to be aligned to R3. Okay. Once I have this alignment, computing accuracy is trivial, right? The numbers within the alignment, those are my true positives, right? So, and to compute the accuracy, I just add up the true positives over the entire set of clusters and divide them by the total number of elements that I have in my data set. So in this case, I would get 11 over 26 as my accuracy. Okay, so it's a fairly convoluted procedure. It's a little bit complex. You start off with a simple alignment, and then you get rid of those multiple alignments in a greedy way. So why are you doing it in a greedy way? Well, if you try to do it non-greedily, the possible number of alignments is huge, and you cannot iterate over that. So that's why you do it very greedily. So now the question, of course, is what was the problem with those multiple alignments? The only reason we do this is because we can't allow multiple clusters to be aligned to the same class. So why is that a problem? Why can't we allow multiple clusters to be assigned to the same class? And the answer to this, it's slightly tricky. It has to do with being able to cheat. This is a particular evaluation framework, right? And as a result of that, you get a number, which is an accuracy. And naturally, you would want your accuracy to be as high as possible. Okay? What I'm claiming is, if you allowed multiple clusters to be assigned to the same reference class, then you could come up with a very, very simple, very dumb clustering strategy that would get 100% accuracy. Can you guess what that is? What clustering strategy would give you 100% accuracy on any data set?
Just one cluster.
I'm sorry?
One cluster.
So the answer is one big cluster. No, that's wrong. That wouldn't work. Yes. So the right answer is you have a cluster for every single data point. Like a singleton cluster for every instance. So imagine, every instance is in its own cluster. So basically this matrix has a ton of different rows, right? And then some columns. And then what is this procedure going to do if you allow multiple assignments? What it's going to do is, for each singleton cluster, it's going to pick the right class. And it's going to assign all of those singleton clusters to the right class. And the overlap is going to be perfect. Right? All of the points in the class will be captured by those singleton clusters. So you're going to get 100% accuracy through this evaluation measure. And of course, singletons are not a useful clustering. Right? It's not something that would be useful to you. So the measure would be cheatable if you allowed multiple cluster assignments to the same reference class. All right, so let's look at the flip side of that. What could I allow multiple classes to be assigned to the same cluster? The opposite of that. So now I'm talking about having two assignments in some row. Is that possible? Is that a good strategy? Could I cheat that strategy? Again, with a very, very simple, very dumb clustering system. Yes, exactly. So that was, so the right answer is you put all the instances into one big cluster, right? So you don't cluster them, you put them all in one huge group. So you have one row in that matrix, only one row. And now because you allow multiple columns to be assigned to the row, all of them would be assigned and you'd get 100% accuracy. So that again would be cheatable. You could create a system that's not a useful clustering system at all, but on paper it'll look like it has 100% accuracy. So that's why evaluating clustering is difficult, and that's why your alignment strategy is actually really, really important. So you cannot have multiple column assignments or multiple row assignments, because both of those strategies are cheatable. And thinking about cheatable strategies, so k-means has non-overlapping clusters, right? But some techniques that we discuss, but some clustering algorithms can produce overlapping clusters. Right? So suppose you have a technique that is allowed to produce overlapping clusters, and let's say you don't allow multiple assignments. So you don't have multiple row assignments, you don't have multiple column assignments, but your clustering technique can produce overlapping clusters. With this evaluation metric, is there a way to cheat? Is there a way to get a guaranteed 100% accuracy with a clustering that's not a very useful clustering? Every cluster be the size of the data set. No, that wouldn't be very useful. But you're kind of thinking it's related to that, yes. Okay. I'm allowed to have overlapping clusters. Suppose my clustering system outputs the power set of my data set, the set of all possible subsets. What accuracy would that have? For every element in the power set, there is a class that corresponds exactly to that element. So if you allowed overlapping clusters, if some system could produce a power set, you would get 100% accuracy. And of course, a power set is not a useful clustering at all. It's like saying, here are all possible clusterings of the data for you, pick the one you like. So all of that goes to say is evaluating clusterings. It's not easy. It's a pretty hard task.